I can hear anyways. All right, so I think most of y'all answered the first two columns pretty easily, pretty straightforward. What would you call the coordinate of -3 comma -3 plus 0i? Page 53. Okay. What is the coordinate for 0 plus 2i? What is the coordinate for 3 plus 3i? What is the coordinate for 2 minus 2 squared to 3i? Very good. All right, we don't actually write the i's. We just note that the b is my complex part. How do I find the modulus? Good. These are all coordinates straight from the origin. I'm not trying to find the coordinate from here to here. I'm all trying to find them basically from this guy right here. Let's see if I scroll down a little bit. Let me. So if you basically connected all of these to the origin, that is the modulus or the distance from the origin that you are looking for. All right. So to do that, we can just use our original equation that we learned in lesson 9 or something like that. Nope, lesson 6. Which comes from the square root of a squared plus b squared. No need to find the difference since you're just coming from the origin. So this ends up actually being the square root of -3 squared plus 0 squared. And what's -3 squared? What's not 0 squared? What's 9 plus 0? The square root of 9. So 3 is the modulus, which is just the distance from the origin to that coordinate. All right, I'm not going to do all the work. This right here would be what? 2, right? This ends up being the square root of 0 squared plus 2 squared. 0 squared is 0. 2 squared is 4. 0 plus 4 is 4. Square root of 4 ends up being just a straight up 2. What about this next one? All right, let's look at that. So 3 squared is what? 9. So we get 9 plus 9, which is 18. So I get the square root of 18, but we need to be able to simplify these. And this is where we'll use the tree. What two numbers multiply to 18? 9 and 2, 3 and 6. Both of them work out. What breaks down into 9? 3 and 3. And then for 6, it'd be 2 and 3. But regardless, what two numbers do we have in common? We have 3. So 2 3s come out as one single 3. And then anything left over will stay inside the house. So your correct answer here is 3 square roots of 2. When you're doing this work, again, if you're uncertain about your answer, just type in the square root of 18, get a decimal, and then type in 3 square roots of 2, get a decimal, make sure those decimals are the same. Then you know you've done it correctly. All right, this next one's going to be a little bit more, so I'm going to write it up here. So I get the square root of 2 squared plus -2 square roots of 3 squared. Now, when I do this work, what is 2 squared? Very good. Now, when I applied this square, I got to apply it to both. What is -2 squared? 4. And then what's the square root of 3 squared? 3. So this ends up being 4 times 3, which is 12. So this ends up being 4 plus 12, right? Which is, and then what's the square root of 16? So the answer here is just straight up 4. Okay. Just know here that you apply it to everything inside the parentheses, no matter how much you got going on there. All right. We got all those answers. Everyone's checked out. I think, like I said, most of y'all have these first two columns pretty much good. It's just got the degree of rotation. So knowing what we know now, let's see if we can just estimate what those answers are going to be. All right. So if I look at Z1, which is right here, again, just so you know, all degrees start on the positive x-axis and then moves along with it. So what I mean is when I'm looking at Z1, I'm going to go from here to Z1 here. How many degrees is that? 180 degrees. Very good. Right. So sometimes we don't have to do all the math that we're about to have to do today. Sometimes we can just physically look at it. Z2 is right here. So let me look at another one. Good. You can see that going from here to here is just straight up 90 degrees. Very good. Any questions so far? All right. Let's do the different colors. Let's do green. Z3, where are you at? Right here. What do we think this is to here to here? It is actually 45 degrees. Do I want to go and show you now? Yep, I'm doing it now. All right, cool. All right, so this is 45 degrees. This one might not be easy to be able to see. This one's 90, this one's 180. So easy to see because it's on the axis, right? We did something in one of those lessons where you had to find out what the complex number is as an ordered pair, find its modulus, and then divide that complex number. It didn't tell you what it was, but that was actually your unit vector you just found. And it was called a unit vector because it puts you right there on that unit circle so you can easily figure out where your answers are. This is what we're going to be doing today. All right. So if, let's say, my coordinate is 3, 3, all right, that's what y'all said Z3 was. What did y'all say my modulus was for that one? What you're going to do is you're going to take that ordered pair and you're going to divide by the modulus. So I get something like this. So to make this a little bit bigger, this is 3 over 3 square roots of 2, comma 3 over 3 square roots of 2. I just rewrote it. Okay. Now let's simplify this guy. What's going to happen to these 3's? They're going to cancel out. What's going to be left on the numerator, though? I heard it. A 1. All right, just because it got canceled out, there's still going to be a 1 in the numerator because the square root of 2 is currently in the denominator's position. But we can't have radicals on the bottom. We've talked about how to rationalize. How do we rationalize these guys? What do we multiply by? That would be for complex numbers. How do we rationalize with just real numbers? Not opposite. That's for conjugate. That's complex. Multiply by what? By its denominator, like straight up. Remember, real numbers that's conjugate is just its same. So there's no numbers that need to be changed. So I'm just going to multiply. Let's do a different color so you can see the work. I'm going to multiply by the square root of 2 on top and bottom. So what's 1 times square root of 2? Square root of 2. I think that's what it said in that yawn. What's square root of 2 times square root of 2? Just 2, right? Because square root of 2 times square root of 2, what's 2 times 2? 4. Square root of 4 is just 2. We've done this enough times where if we multiply by the same radical, the radical just goes away. We no longer have a radical. So now we got square root of 2 over 2. Same process is going to happen over here. And here is my unit vector for my unit circle's coordinates. Well, if we come to our nice special plate that we've made, and I locate the coordinate square root of 2, comma square root of 2 over 2, comma square root of 2 over 2, what is the degree it has next to it? 45 degrees. So to answer, how do we know? By doing this math. So I now know that that's definitely 45 degrees. Which is great because you did. Yes, go ahead. We'll come to that at the conclusion of this week. Or maybe today. I know it comes up somewhere in this week. But that does happen, and we do have formulas for that as well. Unit circle is nice because we can pull the straight answers. If not, we have to depend on a calculator. Now, when I was in school, we weren't allowed calculators in college, but we got a book that was about this tall and about that thick, and it had 4 decimal places for all the square roots, logarithms, and trigonometry that we had to go through to find the decimal versions to do our math. You're lucky, you have calculators, just type in the calculator. All right, so now what I need to know is I need to figure out what in the world is this degree, right? You can have a ballpark idea. Anyone got a ballpark idea? I like it. 1, 3, fit. Okay, yeah. I think it's going to be one of those 3 for sure, between 300 and 330. We have a guess of 315, and I think that's a good guess. And it's going to be one of those three, though, right? Because we know we're in quadrant 4. It's going to be those until it's not. And I'll show you how that works out. But let's do the same math. I'm actually going to pull up because I'm running out of room here. What was that coordinate for D or Z4? This right here. What was the modulus that we calculated? All right, let's take this and let's simplify it up. 2 over 4 just simplifies down to what? 1/2. What's going to happen to this 2, 4? Good. This ends up just going to be a 1. This ends up just being a 2. Do we really need the 1? No. So this is just negative square root 3 over 2. So now that we have our unit vector, let's go to our unit circle. Locate our coordinate of 1/2 comma negative 3 square root of 2. And what degree does it land on? 300. So 315 was a good guess. I probably would have guessed that myself. But in this case, the answer is actually 300 degrees. All right, so that last one was 300 degrees. Questions? We're going to do that math all day long. All right. So let's see where we're at. That was on page 53. We now done the opening exercise. On the red or the one that was on this page? Oh, yes, I can bring that back. I can't bring back the other stuff, though. It might be gone. Let's see. Oh, no, it's right there in front of me. All right, so let's move on to exercise 1 and 2. Good. All right, let's go back. All right, so in exercise 1 and 2, it states on 1, can you find at least 2 additional rotations that would map a ray from the origin through the real number 1 to a ray from the original passing through the point 33? All right. So 3, was what? Which one was that? Z3. So this is looking back at our opening exercise. As Z3, the coordinate was 3, 3. And it's just asking if we can come up with a nether rotation. What was the rotation that we got for Z3? 45 degrees. All right. That is one of infinitely many answers. All right. So what happens with a circle? Like if you have a wheel, what happens? It spins and it keeps repeating the same pattern over and over as you're traveling. So if 45 was one answer and I went an entire rotation across and land back there, what would I have to add to 45 to find out what this degree would be? There you go. So if you are ever asked to find a nether answer for the degree, you could do one of 2 things. Do wheels go backwards as well? So what, instead of adding 360, I could also do what? There you go. So it could be a negative answer. So you can either add 360, and what's 45 plus 360? So 405 would have been another answer, or I could have done 45 minus 360, and that would have gave me negative 315 degrees. So those are two more answers on the answer that we already got. So there is infinitely amount of answers. You can just keep adding and adding and adding. And because of that, we can now produce an equation for just this exercise. And I can say 45 plus 360 times n. And this is a little notation they're going to add. N is going to be in the family of integers. Why integers? What kind of numbers are integers? Not all. What kind specifically? They are real positive and negative whole numbers. So I can plug in positive whole numbers or negative whole numbers, because a negative would end up making that a minus 360, and I would get the same answers. You asking about the z? This? Oh, you never seen that? So this just means n is included. This right here is an integer. Oh, that one, it's a Greek letter E or something like that, but I write it as a C with a line through it. And this right here, this thing right here is just a integer. You have seen the bolded Z, right, for integer? No? I thought we did that at the beginning of the year. We did do it at the beginning of the year. Look back in lesson 1 and 2. We did those. That's not an I. That's a, what's it, a semicolon? Yeah. That's to separate the equation from a fact next to it. Questions? So you can have infinite amount of answers. So again, what the SAT could ask here is, hey, if 45 is the answer, what are other answers? And you just add or subtract 360 until you find one of those multiple choice questions. Yeah, you could do 720 because that'd be 360 times 2. So n's a 2 would be 2 or negative 2. Both of those are integers. You okay with that? Oh. That is an n. Yes, that is a. The n is going to represent any integer. Positive or negative whole numbers is what that comes down to. The 0 is also an integer. So if I plug in 0, I just go right back to 45, which is an answer to. Yes, sir. Oh, I can't just make it a z. I have to say n is included in the family of integers. This z is not a variable. It's a representation of a group of things. Oh, you saying instead of an equal sign? Because that's not how that works out in math. We have to say include it, not just equal. Yeah, I get it. If you put equal on a test, I wouldn't count it off. But on the SAT, you're going to see that notation. Any other questions there? Remember, the sole purpose of this class is to kind of help you prepare for that test. All right, so let's go on to this next part here. Oh, no. If you passed, then I got to get you prepared for college. All right, so in this little thing right here, this is just a bunch of notes, which is nice because you don't have to write them down. But what it's showing here, it's showing you a complex number. If you let A be X and Y be B, that is like your X and Y, your A and B, all the same concept. R, we know, represents our what? The hypotenuse, which is what to us? We did it in the opening exercise. Oh, it will be. The side is, but that, what does it mean to us according to the opening exercise? Well, okay, it's the modulus, right? It's that distance, all right? So that's what that means to us. This is what we're going to be trying to calculate, which is this degree of rotation. Sometimes it's not as easy. And I've actually done the lecture already because I just showed it to you. So that's what it's basically just showing. And then it describes in words. You are familiar with the modulus of a complex number? Too bad it's, ooh, it does have a highlighter. Yeah, I like green, whatever. So you are familiar with this notation? Nope, I don't like that color. There you go. So you're familiar with the Z with the absolute values. That means what? Modulus, distance, square root of a squared plus b squared, square root of the difference of x squared plus the difference of y squared, depending on where your vector is located. We were then able to produce this equation right here. All right, given that z is equal to a complex number a plus bi. All of that is not new to you. What's new to you is this thing called an argument of a complex number. That is just going to be the degree or radiance, and it's going to be noted as the argument or ARG of z. And again, that is going to either be the degree or the radian, which you now have both answers ready to go. Okay. So when you're asked to find the argument of z, you're asked to find the degree of rotation of that said vector or complex number. All right, so new vocabulary for you. Argument of z. Says a whole bunch of other words, but it doesn't really matter. All right, we're good with that? All right. So let's look at an example. We're going to derive a formula for a complex number in terms of the modulus r, which we just talked about is the hypotenuse, is the vector, it's the distance, right? All of those things. And the argument of theta. All right. Oh, that's just, it doesn't give me anything. Hold on. Let me go down to the question. There's your graph. You got the graph. All right. So part A says, what is the value of R and what are the coordinates of the point X and Y in terms of theta? So when it's written out as X plus Y, if we look at this, and we talked about this yesterday, what is this circle? I heard it. It is a unit circle. Why is this called a unit circle? What is 1 unit? The what? Not the radians. What was 1 unit? The what? Not the rays. What was the radius? I mean, what was the 1 unit? The radius, right? The radius goes from the origin to an endpoint of a circle. That is what makes it a radius. So we now know, since I know this is a unit circle, what is the value of 1? Gosh, dog it. What's the value of R? Jeez, my words today. So I now know that this is equal to 1 because it's going to touch anywhere on that circle. It's always going to be 1. So the modulus doesn't move. It's what makes it a unit vector. Caleb, stay with me. All right. So that's that first part there. What is the value of R? Well, R is always going to equal 1. Now, it's wanting to know the coordinates in terms of theta. Go ahead. Because it's a unit circle. It makes it a unit circle because the radius is 1. We can do dilations, and we'll get to that later. But right now, a unit circle is always going to have a radius of 1. Now, if I take that unit circle and I dilate it, then I'm changing the radius, which will change the coordinates position, but not the degree. But you kind of just solved that on the opening exercise. If I quickly kind of draw this, you had this coordinate, what was it, 3, 3? All right. Went right here. This was 45 degrees. Right? But the unit circle is like this, right? So even though this was 3, 3, I was able to take whatever this modulus was, make it a unit vector by dividing it by the square root of, was it 2 or what was the answer? Whatever it was. It was like 2. And so then we simplified that, and that now made my vector land here, which then it gave me now a radius of 1 for that unit vector. And that's what you technically just did when you were trying to calculate the degree. You turned it into a unit vector so we could easily see where did it fall in the unit vector, because that coordinate was actually a dilation of a unit vector. But we just don't, but the degree didn't change. So it doesn't matter as long as we bring it back to its unit vector. We'll talk about dilations and what that affects. And it really just affects the modulus because that's what's dilating, getting bigger and bigger. One more time. That's the first part. R is equal to 1. Then it says, what are the coordinates of the point X and Y in terms of theta? So this is something else you're supposed to learn in geometry as well, but I wrote it up here. You can add it to your plate if you would like. When you're talking about a unit circle, an ordered pair is no longer going to be XY. It's going to be cosine theta, comma, sine theta. So your X value is cosine and your Y value is sine. So if I was to ever ask you, hey, what's the cosine of 45? You would come to 45. And because it's cosine, you would go to the X value. So the answer would instantly be the square root 2 over 2. If I was to say, hey, what's the sine of 315? You would come to 315, go to the sine, which is the Y value, and my answer would be negative square root 2 over 2. All right, so that's what that's going to mean now. So for your coordinate, this was a 2. This was from previous work. I was just bringing it back. It glitches from here to here, so that's why I always stand over here. So the XY coordinate now is going to be cosine theta, comma, sine theta. That is what it means to be in terms of theta. All right. So new notation coming to you, or it's not, it shouldn't be new, but it might be. All right, we good with that? Part B says if R is 2, so now we're talking about dilation, what would be the coordinates of XY? Well, if I'm here and I dilate something, what am I typically doing to that value? Increasing by doing what? What operation? Not adding. If you take a pi and you want to double it, I multiply. So if your radius has now changed or your modulus has now changed, and I want the new coordinates, it's just going to be 2 cosine theta, comma, 2 sine theta. Meaning, if I wanted to double this unit circle, I would take these coordinates, multiply by 2 to both of them. You'll notice that these 2's would then cancel, and I'll now be at the square root of 2, comma, square root of 2, and it'll be doubled its position. Right? You take whatever the unit vector is, multiply by its new modulus, which is kind of what we did in reverse on the opening exercise. Part C then goes even more dramatically. I think it's funny. We don't know it yet because we're just given X plus YI. We weren't given any of those information. We're just trying to develop these equations, and it's trying to get you to the point of the actual equation. What sixth period told me, I was doing that one period, they said I was gatekeeping. They're gatekeeping the formula from us until we get to it. You have to unlock the gate. All right. So if R equals 20, what would the coordinate then be? All right. You'll just take whatever the coordinates are, and you will literally just multiply by its new radius. Questions so far? All right. Now it's getting to a point for us. We're starting to unlock or pick this lock, right? On part D, it says, use the definition of sines and cosines to write a coordinate and points X and Y in terms of cosine and sine for any value of R. What equation would that look like? Not R equals 20, not in this situation. I heard it. I hear it being written down. What is the equation? If I don't know what R is, what was I doing with R each time? Multiplying it to my, there it is. So my generic equation would just be R cosine theta, comma, R sine theta. So if I was given theta and I was given the r, I could tell you exactly what coordinate I'm at now. Right? That's where we're kind of heading towards. Now, with that being said, if I'm told the theta and I'm told the r or the modulus, and I'm able to find the coordinate, then from that coordinate, I should be able to also produce what? Well, that gives me the coordinate, right? So from there, I should then be able to produce the complex number. Right? So given an r, given a theta, I can locate where I'm at on the graph, then also back up and produce the complex number. So to produce this complex number, this would be the x value. So x then would be r times cosine of theta. And my y value would just be r times sine theta. So my overall complex number would be z equals r cosine theta plus r sine theta I. So if you were given the r and you were given the theta, I could literally just plug it into this equation, pop up the complex number. Or the coordinate if I wanted the coordinate, just depending on what information is being asked of me. Do y'all remember taking y'all's BOY? And y'all said there's a target on my question. You remember that? It was like the second or third or fourth question. You're like, I'm just looking at a target. Yeah, I might not. I remember that comment that y'all made. This is what we're about to get into. This is what we're about to get into as in sense of what polar coordinates are. You've been dealing with a rectangular coordinate plane, which is just a rectangle. Polar coordinates is a whole bunch of circles on an X and Y plane. Makes it kind of cool. Alrighty. All right, so that works up all that. And then it goes into, again, some things that you don't have to write down, but basically just writes all this into nicer, cleaner looking stuff. Here's my my Z, where they just factored out the R. I don't normally write it like that. I like to have my R next to everything so I can see that I'm multiplying. R just represents that Z still is my modulus, so that part hasn't changed. So when it gets too warm in here, then we start falling asleep. And this is what we call polar form, right? You have been dealing with rectangular form, which is just an X and Y coordinate. Now we have a polar form, which gives us an argument. So remember, whatever the theta is also noted as the argument of Z. So if you're given this or this, you have both. So all of this is important. And then you already know the rectangular form. It comes from the a plus bi, which gives you the coordinate a comma b. So this part you've already seen. This part is your new stuff. Right? So everyone got the notes highlighted that needs to be highlighted. Alrighty. Feel like I'm the only one excited in here. I love this math. This is good stuff. I don't normally get to teach this until May, and then you're usually burned out by then, so you're not like real invested anymore. All right. So here we go. So let's just kind of fill out this chart and answer the questions. So in this question here, you are given, here's the polar form, here's the rectangular form. You are given the polar form, and it wants it, bless you, and it wants it in rectangular form, right? To get it in rectangular form, all we got to do is the actual math here, all right? So when I ask you what cosine of 60 is, I want you to go to your unit circle that you made yesterday. I want you to locate 60 degrees. Bless you. And since cosine represents my x value, when I go to my 60 degrees, I want to look at the x value of my coordinate. And what is it? That's your answer. Well, it will be, yes. So this will be 3 on the outside, 1/2 on the inside. So you just figured out what cosine of 60 was. Plus, what is sine of 60 over there? Very good. Remember, it is on your circle. I like to put the I there. It just makes more sense. After we've done that, all we got to do now is just distribute the 3. What's 3 times 1/2? So 0 or Z equals 3 over 2, also known as 1.5. Plus, if I multiply 3 times square root of 3 over 2, what does that give me? And that's not how we multiply fractions. That's how we multiply fractions. Not just 3 over 2. Nope. How we multiply fractions here. That's adding and subtracting. That's dividing. How do you multiply fractions? Straight across. Cool. We can finish this off. So 3 times the square root of 3 is what? Can I actually multiply a non-radical with a... So you must write it as 3 square root of 3 over what? 2, because it's just 1 times 2. All right. Braden said I have a few seconds left, so I'm going to go ahead and we're going to go from rectangular form to coordinate form or polar form. All right. So in this situation, I need to calculate my R and my theta. All right. To do that, I need to calculate the R first. R is going to be what? It's going to be 2, right? Because it's going to be 0 squared plus 2 squared, which is just 2. You'll then take these guys, divide it by 2, and you get 0, 1. What is the degree for 0, 1? 90 degrees. So now you know theta is 90. So I get my final answer here as 2 for the R, cosine of 90 plus I times sine of 90. Right? So you have to calculate the R and theta if not given to you. Y'all enjoy the rest of the day, guys.